All right, yeah, perfect. All right, so yeah, so I wanted to kind of start off too, something I wanted to kind of bring up, you know, and it happened in our breakout room, right? And I think it's key to just roll with it. If you're doing these types of events and kids are walking by or dogs are barking, don't get frustrated with it. Everybody's in the same position. You know, in all of the ones that I've been in recently, it's actually turned out to be a great thing. It's almost an icebreaker, right? So roll with it, you know. I think I've gotten to meet more people's kids in this last 6 weeks because, you know, they run up to and they want to talk and everything else. So don't get frustrated with it. Just roll with that. And it's fantastic, especially going back to what I said earlier, in the world that's extremely fake, that's extremely real. And people love that. The people want that. All right. So yeah, this is the second part. This is more of my technical stuff. Let me set up my phone here so I can monitor the time, make sure I stay on time. But since we're not doing questions actively, I don't imagine that that's going to be an issue. All right, so once again, you know, if you enjoy this content, you can check out a bunch of free resources as well as some dirt discounted paid courses as well right now. And so what we're going to look at here are the multi-stage completions for hydraulic fracturing. So these have been really unconventional plays, and they've slangily been called shale plays. So when you hear people talk about shale and they're referring to these resources, what they're actually referring to is a type of rock. So this is the definition from geology.com. I won't read that to you, but what you need to know from this is shale is actually a type of rock. So what are people referring to when they say shale, when they're referring to these unconventionals anyway? They're talking about a low permeability formation. If you're talking about oil, it's typically less than 5 millidarcies. If you're talking about natural gas, you're talking about 0.05 millidarcies or so, just because the increased mobility of natural gas. It's a consolidated formation, so you don't have to worry about sand control. And it can be a shale, but it can also be a sandstone, carbonate, dolomite. It can be a variety of other different formations. What people are referring to when they say shale in the slang form is a reservoir that requires multi-stage hydraulic fracturing to produce at economical rates. So the name of the game in these reservoirs is increasing the contact area. So we have our target reservoir here, and we can drill a vertical well and place it there, and we do increase our contact area, but we can take that well and kick it off vertically and really start to increase, kick it off horizontally, and that lateral really starts to increase that contact. So if you look at the US specifically, typically these plays are anywhere from 100 feet to 500 feet thick. So a 500-foot vertical well compared to a 10,000-foot horizontal well has, the vertical well has significantly less contact. And that's what we're also doing with the hydraulic fracturing. Once again, you can technically do that vertical well. You can put multi-stage hydraulic fractures in it, and it does increase the area. But if you take, let's just call it a 10,000-foot lateral, if you take that 10,000-foot lateral and you put 50, 60, 70 stages in it, now you're really starting to increase the contact area in that target reservoir. So if you're not familiar with fracturing, this is what we're doing with fracturing. So the so here we have the sorry, I know everybody's on mute. Can somebody unmute in the leadership? Can you see my mouse as I'm moving?
Yes, we see your mouse.
Perfect. Okay. Yeah. So if you're not familiar with completions, if you're not too familiar with it, don't worry about the mechanics of it just yet. We'll get into a lot of detail here. But the light gray here, this is the casing. The dark gray here, that's going to be your cement isolating. Of course, you have your target reservoir around it. And then we have a perforation that's already placed in the casing. So they fire the perforation guns, it's penetrated through the casing, through the cement, and now you have regained access to your target reservoir. So once we've done that, we're going to pump our frac fluid down the well, and we're going to create fractures and place proppant in there. So if we zoom in a little bit further on the fracture, we pump in our pad first. That's going to be our clean fluid. And the purpose here is going to create the fracture. Following the pad, we're going to put our proppant into it. That's going to be the slurry. And we pump that proppant into the fracture that we've created. And the reason we do that is because once we bleed off the pressure from the fracture, then the formation is going to try to close on itself. And now the proppant is in place to hold it open. So what we're doing here is we're creating artificial permeability, also known as conductivity. So now with that proppant in place, now we have that conductivity to produce the hydrocarbon through. So why are the multi-stage completions required? It's because the fractures will go to the path of least resistance. So you'll have paths of least resistance due to drilling stresses, drilling damages, friction losses, formation weaknesses. And you can run a barefoot completion, and this was experimented with quite a bit in the beginning, and we proved that we didn't get the isolation needed. And just the curve itself, the drilling stresses and things like that, that creates a path of least resistance. So most of your frac job would go towards the curve and leaving the rest of the lateral with very little or no treatment. And we know that these reservoirs aren't homogeneous too. So this is a sample from the Barnett. This is a vertical sample. It's 150 feet, and this is a mineralogy log. If you're not familiar with the mineralogy log, each of these segments here, that's 10%. So you have 10 going across here, and then all of the different colors here is a different type of mineralogy. So the most prominent ones is the yellow, which is the quartz, the blue checkered, which is calcite, and then of course you have different shades of gray, which those are going to be the different types of clays that you have in the formation. Now just over this 150-foot section, you can see different spots here. So let's start here. You can see this is roughly 10% quartz, about 25% of the calcites, and then 40% of the illite clays, and maybe 10% of the smectite. So, but if we go within to a different section here, let's just go to right here. Now we're looking at about 30% quartz, maybe 15% calcites, and then 40% of the illite type clay. So just over this small section of reservoir, these are going to be very different mineralogies, very different frackability properties. So that also is why the multi-stage completions are required, is because these heterogeneous formations have paths of least resistance already in them because of the different quote unquote frackability of the rock. So that's going to create the path of least resistance, and that's where your fluid and proppant will go. So this is so this has led to 3 completion types being the most effective and the most efficient in these types of plays. That's going to be plug and perf, ball activated completion systems, and the coil tubing activated completion systems. We'll start with the original completion system, plug and perf. This is what Mitchell Energy used to unlock the Barnett and really kind of kickstart this unconventional revolution. And we already have our well drilled in our target reservoir. And once we get out a hole with the drilling, assembly, we're going to run our casing string into the well bore with the drilling rig. Once we get to the intended depth, we pump cement through the casing into the annulus, and the cement will provide the annular isolation between the casing and the target reservoir. Once you're finished cementing, you pressure test, then you can move your drilling rig off a location. We'll zoom into the toe now. So once you've been ready to begin fracturing, bring out your frac crew and your wire line and or the coil tubing. And in this case, you are going to have coil tubing or a workover rig, because we've cemented our casing into the well bore, and you no longer have the ability to pump into this well bore. So it does require through tubing intervention. So you run in your perforating guns with through tubing assembly. Go to the depth of the where you want those perforations, and then you're going to fire your perforations. And once you're finished perforating, pull out a pole and rig down your coil tubing or workover rig. Once you're done with that, then you rig up your frac crew and you begin fracturing your first stage. Now, another alternative that's becoming more common, you don't see the intervention required completion very often. You either see this option here, which is the cementable pressure activated frac sleeve at the toe of the well. So in this case, you're going to make up the frac sleeve directly to your casing, run it in with your drilling rig, cement it into place, and then when you're ready to begin fracturing, you apply the right amount of pressure, the sleeve opens, and you begin fracturing instantly. Another option that's common as well is a wet shoe. So what a wet shoe is is they have the right type of float equipment connected to the casing so the cement doesn't come back into play, or into the casing, I should say. And at the end of the cement slurry, they actually will pump sugar water in the cement. And so what that does is it allows the cement at the toe of the well here to not set up. It remains in a liquid form. And then when they're ready to begin fracturing, they can still pump out of the casing and into the formation to establish that, that connection. So with both the sleeve and the wet shoe, that allows the that allows an interventionless system, and you get rid of that coil tubing or that workover rig. So once you finish your first stage, you've regained access to your well. At this point, now operators go to a wireline deployed assembly because you have the ability to pump in the well. So you pump in your wireline assembly, and that'll consist, of course, of wireline. You'll have your frac plug at the toe of the assembly, setting tool above that, which will set the plug and then release from it, and then your perforation guns above that. So once you get to the intended depth, you send an electric signal through your wireline that activates the setting tool, sets the frac plug, and once the frac plug is set, the setting tool is released from the plug, and you can move your wireline up the well bore. Once you pull up to the depth of your first perforation, you send another electric signal through the wireline. It fires your first set of perforation guns, pull up hole to the depth of your second set of perforations. Another electric signal will fire your second set of perforation guns, pull up hole to the depth of your third. Another electric signal will fire that third set of perforation guns. So this technique here is called cluster perforating. So you're firing individual guns, individual sets of clusters, and you're going to fracture through them all at one time. In this example we're looking at here, this is a 3 cluster per stage example. So with this, with the clusters and the perforation gun specifically, the length is, the new technology with the perforations, you could theoretically do as many of these as you possibly want. It's not a limitation because the electronics, you could do hundreds of individual guns. The practical limitation, though, is the length of the overall assembly at surface. So this will actually be a good analogy, I suppose, on video. So, you know, your perforating assembly here, the longer it gets, the higher, and you remember, you still have to pick it up with the crane and put it into the wellhead. So you have to be able to have a short enough length to be able to pick it up with a crane and get it in the wellhead still. So that's the actual limitation there on the number of perforations per stage. Once you're finished perforating, you pull out a hole with your wireline, you rig up your pressure pumping crew, and you begin fracturing your second stage. And then after that, the process is the same. You're just going to repeat that process. You pump through the previously fractured stage to pump down your wireline assembly, set your plug to isolate from the second stage. Then you're released from it. You'll perforate the third stage, pull out a hole with your wireline, and then fracture the third stage. Run back in with your wireline, set a plug to isolate the third stage, perforate the fourth stage, pull out a hole, and fracture the fourth stage. And then you should repeat that process until all the stages in the well are fractured. So this has always kind of been the Achilles heel of plug and perf, is that wireline run in between stages, because that is non-productive time that your pressure pumping is sitting there idle if you're doing this on a one-off well basis. And this has been improved, and we'll discuss that in a minute. Now with a typical traditional plug and perf job, these are composite plugs. So after you finish fracturing, you do have to go in with coil tubing or a mill out or a workover rig and mill these plugs out. And then once you mill them out, you can put the rig, the well in production. So another way to set this up that's not very common today, but just about the time that I think this type of completion is dead, I hear of another example. So this is open hole plug and perf. So overall, the fracturing process is virtually the same, but the wellbore construction is going to be different. So when you're running on the drilling rig, you're going to space out the open hole packers with your casing string. And that's what will provide your annular isolation, is the open hole packers rather than cement. So you don't have cement here. And the way you're going to run this, so if you're not familiar with casing, each jointed casing is roughly 40 feet. So if you wanted 80 feet of spacing between each stage, then you would run 80 feet. You would run 2 joints of casing here, run your packer, another 2 joints of casing for 80 feet, run a packer, 2 joints of casing, packer, and so on and so forth. So the only real difference with the open hole setup is first at the toe. In most cases, you have pre-perforated casing, but just so that you don't have to have that sleeve or that wet shoe or that a through tubing intervention run to perforate. So as soon as you're ready to begin fracturing, you just start pumping through that pre-perforated casing and fracture your second stage, or your first stage, excuse me. Then after that, the process is exactly the same. The only thing is you have to be more cautious of your depths and make sure that you set your plug and perforate between the open hole packers, since you don't have the cement there, and a little bit more freedom to go up and down the well bore. So like I said, with open hole plug and perf, very uncommon nowadays, but if you're in a situation where open hole is the best isolation for you, then it's an option. I know very few Canadian operators are still doing this type of setup, and then randomly, probably a year and a half, maybe 2 years ago, an operator in the panhandle of Texas reached out to me because they wanted to know more detail about this type of setup, because they planned on doing traditional plug and perf with cement, but as they were drilling the well, they started taking losses, which wasn't expected. So they thought that in their situation, they would not be able to get a successful cement job. So they wanted to use the packers. So with the frac plug deployment, hands down, the most common way to do it is with wireline. Wireline is relatively cheap, relatively efficient, and you can just pump it down through the previously fractured stage. The other alternative is you can use coil tubing or threaded pipe to push the assembly down hole. So before the downturn hit in 2015, some of the higher pressure, higher temperature plays would use this technique, just because the higher pressure, higher temperature plugs were not optimized for pump down. And you had a much higher risk of the plugs presetting during deployment. So that's the primary driver, at least so far, behind any kind of coil tubing deployed system. So the service companies have made several modifications for the horizontal pump downs throughout the year, not only just the plug itself, but also the bypass on the plug. So when you think about pumping down the plug, the wireline assembly, you have to consider the diameter of the plug and the fluid bypass around the plug. So that's where, so first and foremost, the diameter of the plug, force is equal to pressure times area. So the more area you have, the more force you can transmit, and the easier it is to pump down that assembly. The second thing you have to consider is the fluid bypass. If there's enough bypass, the fluid can pump around the assembly, and you don't have near as much pumping efficiency. So service companies have done one of two things. They've either added a pump down kit, which is very simple overall concept. And in a lot of cases, it's a piece of rubber that just increases the diameter that you're pumping against, and therefore reduces fluid bypass, or they've designed their plugs to be a larger diameter to begin with. And if we look at a gun barrel view, it's easy to see the content, excuse me, it's easy to see why this works, because without that larger diameter or the pump down kit, you have a much larger fluid bypass and a much smaller diameter to pump against. But when you add the modifications, you have very little room for fluid bypass and a lot more force transferred because of that larger diameter. You also have the another thing to consider is the fluid distribution through the clusters. So to the right, we have the toe of the well. To the left, we have the heel. Just in case we have some students or people that are just really not familiar with unconventionals, I got asked the question the other day, what is the toe and the heel of the well? So imagine this is the well here, right? So this is the vertical portion of the well that connects the surface, and this is the lateral. So it's a foot. So the end of it is going to be the toe of the well, and here at the joint, that's going to be the heel of the well. or at the curb, I mean, it's the hill of the well. So as we're fracturing, we assume even frac distribution because it's the best place to start, I guess is the way to say that. However, realistically, we don't get that. So we assume in our basic theory of frac design, if we're pumping 90 barrels a minute at surface, we're pumping 30 barrels a minute per cluster. So keep in mind you have friction losses between each of the perforations as well. So realistically, just because of the friction losses, you would have a frac job that looks something like this. Where the heelmost perforation takes the most amount of fluid because it has the path of least resistance, because the fluid doesn't have to travel as far down the pipe and it's less friction. And then the toe-most perforation receives the least amount because it has the most amount of friction. So that's where a technique called limited entry perforating comes into play. So this is just an extremely simple example. It's easy to visualize, just to give you the concept of what limited entry perforating is. What we're doing here is we're changing the number of holes of perforations per cluster. So we have five perforations at the toe-most perforation, 4 in the middle, and 3 back towards the heel. So now by default, the flow area, changing the flow area, the toe is the easiest for the fluid to flow out of, and the heel is the most difficult because it has the least amount of flow area. So if you do your limited entry correctly, then theoretically you go back to getting that even distribution because you balanced out the amount of friction each perforation has versus how much fluid volume, flow area that you have for each cluster. So you want to try to balance out that energy. And like I said, this is an extremely simplistic example. You can do this with number of holes, diameter of holes, different things like that. Now, even if we do the limited entry, we're only focusing really on what we can control as far as friction losses and the mechanical things. The reality is these are not homogeneous formations, so we're not going to get even distribution. So what happens when our frac job looks something like this? And that's where diverters come into play. So now we've got a 6 cluster per stage, and the more clusters you add per stage, the more likely you are that you have that uneven distribution. So once again, a very simple example of diverters. It's actually a lot more complicated than this. This is the easiest way to show you the general concept. So here, this operator would assume that basically each one of these clusters is an individual stage. So they pump down their frac job. They assume that their fluid goes out of one individual cluster. So they pump, quote unquote, stage 1. And then when they're finished pumping that volume, they pump down a diverter. It blocks off near wellbore at the perforations, and it forces the fluid to divert into another cluster. Once they finish pumping, quote unquote, stage 2, then they pump another diverter down. It blocks off near wellbore there, and it forces the fluid to go and divert into another section. And then you're just going to repeat that process. It depends on what kind of diverter you're using, but so you may have to go in through tubing and mill it out and wash it out. And some of them are dissolvable, so they'll remove themselves from the well and without any intervention. Now the problem is like I said, that's the simple example. That's the easiest way to visualize it. But what happens when we go back to this well here, where you already don't have even distribution? It's not going out of one. And in most cases, this is going to be more likely to happen where you have a couple of dominant perforations. So what happens here when we pump diverter 1? So it blocks off the most dominant perforation, but what happens here? And because this one was already dominant too. So now this one's going to become more dominant. And then what happens if you pump another diverter and it blocks off a non-dominant perforation? It's done the complete opposite of what it was intended to. Now all the dominant perforations are going to be even more dominant. And then you also have to be careful how much diverter you pump down too, because you pump down too much diverter, you'll block off the entire stage, and you'll have to do a through tubing intervention job to recover. So diverters are definitely as much an art as they are a science right now. A lot of experimentation going on. I've seen operators get really crafty with things. For example, I talked to an Eagleford operator. Their diverter strategy was they had a 10 well pad. They considered it a test pad. They did analysis on it, and their conclusion was that they got 40% perforation efficiency downhole, which means that 40% of their fluid, that 40% of their perforations accepted a large majority of the fluid in the proppant. So going forward, using that data, they would pump 40% of their frac job per stage. They would pump enough diverter to block off 40% of the perfs, and then pump the remaining 60%. Some operators kind of consider it cheap insurance, which in today's time, there's no such thing as cheap anymore. So the operators that were doing this may very well kick this strategy out the window to save more money. But they were kind of skeptical as to whether diverters worked in the first place. So just halfway through their frac job, they would pump diverters and hope that it did something. So this is a great article here by the SPE magazine, JPT. It goes through 5 case histories of diverters, and they have all sorts of mixed results. If I recall correctly, it's 5 case histories. 2 of them, they believe that they had mild improvements or moderate improvements in production. So they thought they were effective. 2 of them, they didn't really see anything better or worse about production on the wells. And then 1 of them was kind of a train wreck. It was one of the ones that they actually did have the diverter blocking off non-dominant perforations and creating more dominant perforations or more dominant fractures that got further and further away from the well. So a lot of experimentation being done, a lot of questions still out there about diverters right now. But, in a lot of cases, diverters are growing in use as well. And the reason is you can get fewer stages with the same number of clusters. So you can take, let's just go back to the simple example, 3 clusters per stage. So the operator in their traditional completion design, they had 2 stages over this length with 3 clusters per stage. Now they can go in and do 6 clusters over 1 stage. So they reduce the number of plugs and they reduce the wireline runs. So just to keep it simple, they pump down their job, they pump half of it, then they pump enough diverter to block off half of the perforations, and then they pump the other half of the job to get the distribution. And in both cases, this is the same well design. So the top one, you might have 50 stages with 3 clusters per stage for 150 clusters in the well. And the bottom one, you could have 25 stages with 6 clusters per stage for 150 clusters. But now the bottom well has half the plugs, half the deployment time of wireline, and you're going to have some savings on millouts as well, just because you don't have near as many plugs to mill out. So with all this complication, why do we use cluster perforations to begin with? Technically, it's possible to do single entry plug and perf. You run in, fire a single set of perfs, fracture, plug, single set of perfs, fracture, plug, and so on and so forth. The reason we use cluster perforations, though, is for efficiency. So this is from a prominent Permian operator. This is from their Q1 of 2016 operator presentation, their completion optimization strategy. They had a 9,000-foot lateral, 100-foot per stage with their spacing, 15-foot cluster spacing. So just a reminder, the stage spacing, the 100-foot stage spacing means it's 100 feet from plug to plug. The 15-foot cluster spacing is going to be 15 feet between each individual cluster here. So what that information translates into is that's 90 overall stages, 6 clusters per stage, and that's 540 total injection points in the well. Now, if you assume 2 hours of downtime to run your wireline, set your plug, perforate, and pull out a pole with wireline, 90 stages would be 180 hours or 7.5 days of downtime, assuming you had a 24-hour crew. But if you try to break that into 540 stages, that would be 45 days of non-productive time with your pressure pumping crew. So it's a significant savings by adding these clusters in. And just to stick with this 540 injection point example, you could, to get that 540 injection points, you could do 180 stages with 3 clusters per stage. You're going to have 15 days of wireline time. 90 stages with 6 clusters per stage, 7.5 days of depth wireline, or you could do 45 stages with 12 clusters per stage, and that's 3.75 days of downtime. So, and you also have the significant cost savings there: 180 plugs at the top, 90 plugs in the middle, and 45 plugs. So this is why we're seeing this in the completion optimization. Now, this is also something else to help efficiency here is simultaneous fracturing operations, also known as zipper fracturing. So what we're looking at here is 2 different wells. This is the aerial view. So if you're standing at surface, you look straight down, we're actually looking at the laterals going out here. So when you run wireline on well B, you run your pressure pumping on well A, and then you swap the services over. Run wireline on well A while fracturing well B, and then switch them back over. Wireline on well B while fracturing well A. And this way you start reducing the downtime between stages, reducing and or eliminating. So you rig up your frac crew, you rig up your wireline crew. They're close to each other on the wellheads. These wellheads may be 10 or 20 feet apart. On the frac crew side, you have a manifold set up. So it's just a matter of turning a valve to control which flow goes to which well. And with the wireline, it's just a matter of swinging the crane from wellhead to wellhead to determine which well is receiving wireline. So that helps you not have wireline completely idle the entire time you're fracturing, and not have fracturing completely idle while you're running wireline. And you can also apply this on a large scale. So you bring out enough frac crews and wireline crews that you can start implementing this on these larger pads. And if you do it, and some operators are reporting this, if you do it enough, that they've optimized it to the point where they've eliminated all the non-productive time between stages all the way around. And also, if you're in a pad where they actually did skid drilling, mounted the drilling rig on a skid and just shifted it across, you can also do the same thing with pressure pumping and wireline units, mounting them on a skid rather than having to move them between each well. So this is really, and this is kind of one of the biggest points I keep talking about, the analysts that are just doom and gloom on the U.S. shale. This wasn't in large, especially in the Permian Basin specifically. The Permian was new in 2015. We had not implemented all these strategies. And once you start eliminating that non-productive time and putting this on a large scale, in my opinion, there's just no way that it was still $50 or $60 break-even costs that we had in 2015. We've gotten really good. We've gotten really efficient. And I don't know what the actual break-even cost of the wells need to be in the Permian, but I think they're a lot lower than they were in 2015. Some of the newer technology with plug and perf is the disintegrating frac plug. So with this, it's overall the same concept as a composite plug. You set the plug, you can still pump through it when it's set, and then you pump a ball down hole, and that's what provides isolation. But in this plug, you don't have to mill it out. In the wellbore fluids, both the ball and the plug will remove itself from the wellbore without intervention. So it helps eliminate that mill out after the plug of the plugs after the well's been fractured. The disintegrating materials make it the post-frac interventionless, and you also have the full production diameter afterwards. Now, there are some operators that are using the dissolvable plugs in a full wellbore, but in most cases, it's more of a hybrid system where they'll run the dissolvable plugs outside of coil tubing range where they can't mill, and then they'll run composites within coil tubing range. That way they can mill out the composites after the well's over and within that safe operating range of coil tubing, and then the wellbore fluids will remove the dissolvable plugs at the toe of the well. The next completion we have is the ball activated system. So there's a couple of different ways to set this up. Your key features are going to be your open hole packers. That's your primary way to, at least in the traditional systems, to get annular isolation. You have your ball activated sleeves, and then your casing packer is a secondary component, because as long as it can hold the pressures and temperatures of the weight of the completion below it, it doesn't really matter what your casing packer is. Now, the nomenclature here is going to be the same as plug and perf. It is going to be a toe to heel fracturing. So stage 1 will be at the toe, and then you'll work your way back up towards the heel. There's a couple of different ways to set this up. The first one is the fluid activated packers. So we've installed our completion system. Once we're to depth, we pump our fluid through the casing into the annulus, and then we set our casing packer. So these are the fluid activated packers. Once you've pressure tested with your drilling rig, then you can move your drilling rig off a location, and over time that fluid will activate the packers. They swell out and they contact the formation to provide that annular isolation. Once you're ready to begin fracturing, bring out your frac crew, drop the first ball in the system, pump it down hole, and then once it lands on seat, the sleeve shifts open and you begin fracturing your first stage. The other way to set this up is hydraulic set packers. So with this system, you're going to have 2 additional tools at the toe. The first one being your isolation tool. So once you get to the intended depth with your drilling rig, you drop the first ball. That's going to correspond with your isolation tool. Once it gets down hole, you pressure up, it closes the isolation tool, and now you can no longer flow into the well, and you have a point to pressure up against to set your equipment. So you raise your pressure, you set your casing packer, continue raising your pressure, you set your open hole packers, and then once you've done that, you can pressure test with the drilling rig and move the drilling rig off a location. The other tool that's at the toe is the pressure activated frac sleeve. So that isolation tool is closed off. We can no longer pump into the well, and we also can't do intervention because there's ball seats in all of the sleeves, all of these sleeves up in the well. So in most cases, it would be very difficult to get through tubing to open the sleeve. So that's why it's pressure activated. Once they get to once you're ready to begin fracturing, you apply the right amount of pressure, the sleeve opens, and you begin fracturing your first stage. So we'll zoom in and take a little bit closer look. So we've zoomed in on the second sleeve here. Overall, this is a very simple tool from at least a conceptual standpoint. You've got ports on the outside. If we look at the cutout, we've got an insert here that covers up those ports when it's in the closed position, and a ball seat profile in that insert. So as you're fracturing your first stage, you're pumping through all of the ball seats above it. Once you're finished fracturing the first stage, you're going to drop the ball that corresponds to the second sleeve, pump it down hole, it lands on seat, shifts, applying pressure shifts the sleeve open, and then the ball and ball seat isolate from below and force the fluid to divert out of the second stage frac sleeve. If we move up the well to the third sleeve, as we're finishing fracturing our second stage, we drop the ball that corresponds to the third sleeve, pump it down hole, lands on seat, applying pressure, shifts the third sleeve open, isolates from below, and you begin fracturing your third stage. Now, it's a little bit difficult to tell in the animation, but each of these stages gets incrementally larger. So the first stage at the toe of the well will be the smallest ball in the system. That way it can pass through all of the ball seats above it. And then they get incrementally larger as you go back up the well bore. And the procedure is the same. You just continue dropping balls, drop the one that corresponds to the fourth sleeve, pump it down hole, pressure up, shift the fourth sleeve open, and begin fracturing. And then once you're finished up, drop the ball that corresponds to the fifth sleeve, and just repeat that process. So this has really always been the highlight of this kind of system. It's very efficient at surface because you don't ever have to shut down your frac job. You slow down to drop the ball, but it's a continuous pumping process. If we zoom back in for the sleeve, the post-frac operations, you're going to produce through the fractures you've created, back through the ports you fractured through, and then production from below will push that ball off seat and back towards surface. And in a lot of cases nowadays, that's actually a disintegrating ball. So it'll disintegrate in the well bore and not come back to surface. Now, technically post-frac, this can be an interventionless system, but as you can see, you do have diameter restrictions here. So if that is an issue, these are designed to be short and compact, and in most cases a cast iron material. So you can go in, mill out those ball seats relatively easy, and get your near full production diameter. So this is a case history. This is a case history here. This is 2013 in the U.S. Bakken. This is a 50-stage system. You can see all the parameters here, but really where the focus is a 50-stage system took a total of 51.2 hours to fracture from opening the wellhead to shutting it back in. And that also included 4.5 hours of downtime. So actual pump time was 46.7 hours. Now, by today's standards, that's a really small frac job, but because of that nonstop fracturing, it shows how efficient this system is. You also have cemented ball activated frac sleeves. So same overall concept, only the wellbore construction is different. You remove the packers. Once you get to the intended depth, you pump cement into the annulus. But after that, the process is the same. When you're ready to begin fracturing, you apply pressure to open that cementable pressure activated sleeve, and then you're just going to drop balls in the correct order, and the frac process looks exactly the same. You do have to consider, though, a couple of things when you're cementing the plugs. So with this system, with just traditional cementing operations, you're going to pump your cement through your casing, and you follow it with a cement wiper plug, which does exactly what it sounds. It wipes the cement from the casing and makes sure you don't leave cement stringers. It's no different when you have the cemented sleeves, except for now you have a ball seat diameter to go through. So you pump your cement, and now you still have to have that wiper plug, but it has to be able to pass through that ball seat and not get stuck and prematurely open that sleeve. So you are limited on how many sleeves that you can run, because you can't get down to too small of a diameter. So right now it's about a 2-inch diameter is the smallest, which caps you at about 25 to 30 stages available with these sleeves, depending on your service company. But to kind of combat the limited number of sleeves that you can have with cement, there are also cemented sleeves with multiple entry points. So with these sleeves, pretty much the same concept, but now one ball will open multiple sleeves. So you drop the ball, it opens this sleeve, passes through, opens this one, passes through, and opens this one, and you fracture all 3 of these at the same time. Drop another ball, the next size ball, opens all 3, and you fracture at the same time. So this is very similar to plug and perf. This is multiple clusters that you're fracturing through all at one time. Now, if we zoom into the sleeves themselves, a little bit unique features compared to the traditional ones. First off, you have adjustable frac ports. Because these are designed to kind of mimic plug and perf, then the ports are as well. So you have them 360 degrees around the sleeve, spaced out with different phasing options. And you have a lot of things you can do. You can block off ports if you don't want those ports there. So you can do limited entry techniques by limited to the flow area. And you can also change the size and the diameter of the ports. You can make them larger or smaller. And so that allows you the ability to change diameters, adjust phasing, and everything else. And if we look at a cutout, very similar to the traditional sleeves, the only difference is, at least the ones that allow the ball to pass through, when the ball lands on seat, you apply the pressure, it shifts the sleeve open like the other one, but now it has a profile in the back and will allow that ball seat to subside and the ball continue moving down the wellbore. And this is hands down where these sleeves are being run the most commonly, is a hybrid system with plug and perf as well. So this is going to be in longer laterals. They'll run the clusters at the toe of the well. They'll drop the balls to fracture, just like you would in standard operations. And this way it's interventionless. They don't have to get wireline down there, and then after the job, they don't have to get coil tubing down there to try to mill out. So that's why you're going to see this as a hybrid system in a lot of longer laterals. Above the sleeves, you do your traditional plug and perf. And then, like I said, this is the entire purpose, is to have a completely interventionless system at the toe of the well outside of your coil tubing range. You also have the reclosable sleeves. You can go back in, mill out the profiles, the ball seat profiles, and then once you're finished milling out, you go in with coil tubing tools and you can reclose them. So this is handy in a water shutoff situation, and it also has some benefits in refracking. And a couple of the newer techniques out there, the frac sleeves with a counter mechanism. So what we have here, we have 5 different sleeves. This is all the same profile, the same ball seat size, but it allows the ball to pass through. And as the ball passes through each time, it counts down. So now the ball is on sleeve 0. You apply pressure, it shifts the sleeve open, and you begin fracturing that first stage. Now you drop the exact same size ball again. It goes through each one, it counts down, and now this sleeve is on stage, on counter 0. So when the ball hits it, it's in the activated position, apply pressure, shift that sleeve open, and begin fracturing there. And then you do the same thing, drop another ball the exact same size, and now this is sleeve 0. So that's what, so there's a couple of different ways in this version here. This is going to be mechanical, but there's also electronic versions. And there are a couple of sleeves out there that are a combination of mechanical motion and electronics that gives it this functionality. And what we're trying to do with these new sleeves is get virtually an unlimited number of stages with little to no diameter restrictions. Another newer technology is the ball seats with the collet locator. So now the overall sleeve has about the same functionality, but the insert doesn't have the ball seat in it. Instead, it has a profile. So with this system, we actually pump the ball seats in the well. We have that collet profile that's built into the that's built into the insert on the sleeve, and you have the collet on the ball seat itself. And then of course you already have the ball on seat, which is what gives you the capability to pump down that ball seat assembly. Now in this case, the collet profile is not the right size for the collet, so it does not snap into place, and it continues moving down the well bore. Once it gets to the correct collet size, then the collet will snap into place, and you apply pressure against the ball seat, and it shifts the sleeve open. So overall, it's the same functionality as the ball and ball seat. Just you're pumping it into the well instead of installing it with the original completion. So now you can fracture. Once you're done fracturing, it's a dissolving ball. And then afterwards, if you want to, it's a large diameter ball seat, so you can leave it in to produce through. But if it is going to cause you issues, you can go in and retrieve that collet, that ball seat with the collet on it as well. And so you can retrieve all of those, all of the ball seats from the well to get a full diameter. You also have the, and then the third type of completion, the coil tubing activated systems. So we'll start with the sandjet perforator, even though it's not very commonly run anymore. You would set this up like a plug and perf well, run your casing in, cement it into place. Once you're done cementing, do your pressure testing, and then you can move the drilling rig off the location. Once you're ready to begin fracturing, you bring out your coil tubing and your frac crew, run down your coil tubing assembly, which the key components, of course, will be coil tubing. And you also have the coil tubing packer and sandjet perforator. Once you get to the intended depth, you're going to pump an abrasive slurry mix through the coil tubing out of the sandjet perforator, and that's going to abrasively cut through the casing, through the cement, and regain access to your reservoir. After you're done fracturing, after you're done sandjet perforating, you shut down the flow through the coil tubing, and now you're going to pump through the annulus and out of those perforations you've created. Because your primary frac is done through the annulus, that's why you'll hear this type of system referred to as annular fracturing in a lot of cases. Once you're finished fracturing, pull to release the packer, move up the well bore, reset your packer for isolation from below. You want to pump that abrasive fluid through the sandjet perforator, create your second stage perforation, then you shut down again and pump the second stage through the annulus. Pull to release the packer, and then you move up the hole to the third stage, and then you just repeat that process. Setting the packer, sandjet perforating, and fracturing. And you just do that until all stages are complete. Now the primary way to do this is using the frac sleeves. So we've got our system to the intended depth. Once we're done, or once we're there, then we pump cement through the casing into the annulus. And this type of system was originally designed as a cemented completion. So once you've finished pressure testing, move your drilling rig off a location, and then you're going to run your, once you're ready to begin fracturing, bring out your frac crew and coil tubing, and run the coil tubing to depth. Now overall, the assembly looks very similar to the sandjet perforator, even though the sandjet perforator is not the primary means of of regaining access to the formation. And we'll see a couple of benefits here in a minute. So we locate the first sleeve, open it, fracture through the annulus, pull up hole, locate the second sleeve, set the packer, open the sleeve, and begin fracturing down the annulus. And then we'll repeat that process, opening all the sleeves and fracturing them. Now, one of the first benefits of the sandjet perforator is if we decide we want to add a stage during the frac job between these two sleeves, then we have the ability to do so by sandjet perforating that stage and adding it on the fly. So it gives you some ability to adjust during the frac job. There's a couple of different sleeves out there. The first one we'll look at is a pressure open sleeve. This is one of the more common ones. You locate your sleeve, you set your packer into that insert, and then and once it's connected with those slips, now you're connected to the insert. So if you apply annular pressure, then that transmits force onto that insert, shifts the sleeve open, and that's how you begin fracturing with this sleeve. The other type is the pressure balanced frac sleeve. So with these, you run in, you locate your frac sleeve, you set your packer, and these sleeves have ports, internal ports above, at the top and the bottom of the sleeve. So when you apply pressure down the annulus, let's just call it 5,000 PSI. So that top port there sees 5,000 PSI, but the bottom port does not because the coil tubing packer has it isolated. So that creates a pressure imbalance and allows the sleeve to shift open. The other sleeves in the wellbore, though, both the top and the bottom port see that 5,000 PSI, so they remain in a pressure balanced position and in the closed position. So with the locating the sleeves, the original way to do it was a casing collar locator. So if you're not familiar with casing too much, if you're using a low grade casing, you have one jointed casing here, another jointed casing here, and this is the connection. So this is the casing collar connection between the two joints of casing. And you can see there's an actual gap here. So it doesn't make up flush. So the casing collar locator, you can see here, it's got two sides to it. And on the way down, it's got a very low edge. So it goes right through the casing collar and doesn't catch. But as you're pulling back up the wellbore, that casing collar locator has a almost 90-degree hard stop. So it does spring load snap into place, and it actually requires some force to pull out of that casing collar. So it'll require about 2,000 pounds of force, and then you can pull that casing collar. So you actually have to stop, pull, and move. So the way you would locate originally, you pull up your wellbore 40 feet, you'd catch a casing collar, 2,000 pounds of force, pull up hole another 40 feet, casing collar, another 2,000 pounds, 40 feet, and then you catch there. And below the sleeve, you would have a 6-foot putt joint. So right now you need 2,000 pounds of force to pull out. You move up hole 6 feet and it catches again. So that's how you know where you're at with your coil tubing, is the length of the casing around the sleeve. The problem with the casing collar locator is that in these horizontal wells, it may take 2,000 pounds, more than 2,000 pounds of force to even move the coil tubing because of friction and everything. So in most cases nowadays, you're going to see some sort of custom frac sleeve locator where it snaps into the frac sleeve and requires something significant to actually release it. That way, when you're snapping into place in the sleeve, your packer and your equipment is in the correct place to open the sleeve. So we zoom back into the fracturing operations real quick. We've opened our sleeves. We fracture down the annulus. And there's a couple of things. So when you're fracturing down the annulus, that's creating a collapsing force on the coil tubing. So through the coil tubing, in most cases, you're not actually going to contribute to the frac job, but you will pump through the coil tubing first and foremost because it allows you to put back pressure against the coil tubing and that collapsing force and protect the coil tubing. But it's also at a very low rate, maybe a half a barrel a minute. And it's the injection point here is right at the injection point of the sleeve. So that allows you to get a dead leg pressure reading. So the pressure you're reading through the annulus, there's a lot of friction against the coil tubing and the casing. There's this turbulent flow. And so what you're reading at surface with the casing may not be actually what's going on here at the injection point. But this is laminar flow through the coil tubing. It's less friction. So what you're actually reading through the coil tubing at the sand jet perforator is pretty close to what's actually going on downhole. So that gives you a minute, that helps you avoid a screen out. It allows you to see the pressure rising earlier and adjust for a screen out. But if you're in a situation where a screen out occurs and you can't catch it in time, you also have a contingency option built in here. And just real quick, a very simple explanation of the screen out is you physically cannot pump your proppant into the fractures anymore because it doesn't have enough fracture width. So now all of your proppant is starting to back up into your casing, and eventually you lose the ability to pump out of that stage. So if this happens, you unset your packer, you can shift your coil tubing up and down the well a little bit, and you have the ability to circulate through your coil tubing out of your sand jet perforator or a circulation sub, remove the excess sand, and then you can move on to the next stage and resume your frac job with minimal downtime. Some of the newer technologies for these systems is the reclosable sleeves, and in the primary frac, you can use it as well. So you go in, you shift the sleeve open, apply the frac job down the annulus, and then once you're finished, you reclose the sleeve and move on up to the next well, or excuse me, the next sleeve. Locate the second sleeve, open it, fracture down the annulus, and just repeat that process. Then after you're finished fracturing, you go in and open them all for production. Now, the reason that you might do this is, first off, and this is going to be very formation dependent, depending on how quickly your formation will close and hold that proppant into place. But if it takes a while for the formation to do that, then once you shut down your frac job and bleed off that pressure to move on to the next stage, then you have a risk of your proppant flowing back into your well bore. So that's the first reason you might want to do it in the initial frac. Another interesting concept, and I know there's been some experimenting with this, everything we've talked about so far has been a toe to heel frac job, just because of isolation issues. But with these sleeves, you can go in, we'll start at the heel, or excuse me, the toe still. We'll fracture the first stage, reclose it, and then for our second stage, we go to the third sleeve. Locate the sleeve, open it, fracture down the annulus, and then we reclose it. And because we can reclose and isolate there, now we can go back downhole to the second sleeve for the third stage and fracture there. So what this allows you to do, what they're attempting to do here is play on stress shadowing effects and try to get a more complex fracture network by doing out of order fracturing rather than just a toe to heel fracturing. So it could be very interesting to see the results from that. Afterwards, same thing, you open back up, and now you're going to produce through those sleeves into the well. Now this was originally designed as a cemented completion, but it's easy to convert to an open hole completion too. You just put put packers between the sleeves to get the annular isolation. Okay, so that's the three primary types of completion systems. Yeah, I'm doing pretty good on time. Three primary types of completion systems. So what we've discussed so far, each of them provides effective multi-stage isolation. We have the numbers to prove that. Each of them does require different services. Any of them now can be cemented or open hole. You can do open hole plug and perf. You can do cemented sleeves. And any of them can also divert with multiple or single entry points. You can do single entry plug and perf. You can do multi-entry sleeves. So how do we choose the right completion system? So we'll go through benefits and consideration, and these are the metrics we're going to go through here. So we'll first start by number of stages. Plug and perf, virtually unlimited number of stages. The limitations are going to be the length of your coil tubing and the ability to remove plugs. You also could extend that ability by using a workover rig to remove the plugs because you can get in those longer laterals. And you also, a lot of operators use the hybrid system that's interventionless towards the toe, so that they don't have to intervene and mill out those plugs. You have the ball activated systems. There is a finite number of ball and ball seats with the traditional blends. And most of these systems are designed for 4.5-inch casing. So that's the numbers we're going to use. Theoretically, you have a few more stages with 5.5-inch casing, but just because of the nature of the balls, the larger they get, the weaker they are. So it's not going to be many more stages, even in 5.5-inch casing. So if you're looking at a 10,000 PSI rating, about 40 stages. If you can live with a 5,000 PSI, you can get about 65 stages, or if it's less than 5,000 PSI, I should say. And, if you have to restrict your diameter to 2 inches because you're cementing it, it's going to be less than 30 stages in most cases. Now, the new sleeves we talked about, though, the counter sleeves and the collet style, those are offering virtually unlimited number of stages with little or no diameter restrictions. Then we have the coil tubing system, virtually unlimited again. The limitation here is going to be the length of your coil tubing and the ability to function in long laterals. You have to be able to locate the sleeves. And so you could use a workover rig to extend that length, or you could use a hybrid system that's interventionless towards the toe as well. That way you could just drop balls with the frac sleeves at the toe, not mill out afterwards, and use the coil tubing sleeves towards the heel within the operating distance of coil tubing. So we also have the stage placement while fracturing. So what we're looking at here, and this was a situation I had in a well in the Marcellus that I was on. They had a huge fault in the well bore that they didn't realize they were going to have at first. So if you get in a position where you need to avoid a section of a well, and maybe you didn't have the knowledge ahead of time that the fault was there, then during the frac job, you can simply pull up hole, set your plug away from that fault, isolate that section, and finish the rest of the well. So it's just because you haven't fired your perforations yet or placed a sleeve, then you have complete flexibility. You just move your wire line up the well bore 200, 300 feet, whatever it needs to clear the fault. Now, with the ball activated systems, you don't have that ability. So the only thing you can really do here is try to isolate it with your open hole packers and then just skip over that stage or the stages that are come into contact with that fault. So you just drop the next size ball and you finish fracturing that way. And then with the coil tubing system, same thing. You don't have a lot of flexibility as far as you've already placed these sleeves, so they are where they are. But if you need to, you can skip over sleeves and avoid that fault as well. Then we have design flexibility while we're fracturing. So how much flexibility do we have? So with plug and perf, it's just a cemented casing string. So you can do whatever you want in this. So you can do whatever spacing you want, whatever cluster number, cluster spacing that you want to do during the frac job on the fly. And, especially today and probably likely what we're going to see going forward, you have drilled but uncompleted wells. And some of those drilled but uncompleted wells sit for 2 or 3 years, and a lot changes on completion design in 2 or 3 years. So the additional benefit here is if your original completion design when you drilled the well was a 3 cluster per stage design, but now you've swapped to a 6 cluster per stage, you can still do that. You have complete flexibility to adjust to your modern day completion design with plug and perf. With the ball activated systems, the completion equipment is all set. So if you originally ran a 25 stage system, but now you like to run a 50 stage, it's not possible to do. You just have to work with what you have already in the well bore. And with the coil tubing systems, you are somewhat fixed into place, but you do have a little bit of flexibility if you have the sandjet perforator, or with the sandjet perforator, I should say. So you have to fracture where the sleeves are, but if you needed to add additional wells, or additional stages, then you could sandjet perforate to do so. So the other thing to consider with all this is contingency options. So if we have plug and perf, if we have a screen out during plug and perf, and we can no longer pump into the well, we have a full diameter above it, so we can go in with intervention tools we wash out that screen out, and we have the ability to regain access to the well. So it does require a through tubing trip, but you can have the full suite of coil tubing tools. Now with the ball activated system, if we have the same screen out, then it really depends on where you can screen out, So you could run in with a coil tubing tool and set up a ball looking system and manually open one of the sleeves. And in this case here, we're only going to skip over one stage. So we're not losing a lot in the well. The problem is how many stages will be lost because this is not the case every time. So let's just say we had that 65 stage system and we screened out on stage 1, then we're not going to be able to get that coil tubing down hole, this intervention tool, all the way down to stage 2 to open it. It's going to be a 2-inch minimum depending on what size diameter coil tubing you have. So if you can only go down to the 2-inch ball seat, then you may skip 30 stages in the well. So it really depends on your what you want to do there. Worst case scenario, if it's too many stages lost, you could go in, mill out all the ball seats, and then do an open hole plug and perf between the packers. And then with the coil tubing activated systems, we just looked at this. If you screen out, you can go through through the coil tubing, circulate through the annulus, and recover relatively quickly. Operational efficiency with plug and perf. You have to pump down the assembly, set your plug, perforate, pull out a hole. So it's very inefficient if you're doing it on a one-off well, depending on how good your wireline crews are anyway. But you also have the simultaneous fracturing that helps improve the efficiency. So once you start eliminating some of that wireline downtime and some of that fracturing downtime, then that can really help out there. You also have the ball activated system. The highlight of this system is really the operational efficiency, because you're just nonstop fracturing, pumping the balls down hole, and very effective and very efficient at surface. With the coil tubing activated system, you do have to briefly shut down between stages, pull to release the packer, locate the second sleeve, and open it. Overall, that's pretty quick, depending on how, obviously, the distance between the sleeves and then also how good your crews are. But you may be looking at anywhere from 10 to 20 minutes between stages with this system. You also have to consider services required for fracturing. So obviously all of them require pressure pumping. And you also have wireline with plug and perf. And then of course your coil tubing. So it depends on how you've set up your tow. You potentially may need it for plug and perf if you have to go in and do through tubing intervention. And of course you have to have it for the coil tubing activated sleeves. So you also have to take this and all of that into consideration as well. So are wireline units available? If you're in U.S. land, asking if wireline units available may be silly, but if you go international to some of the emerging markets, it's something you have to consider. Also, are perforation guns accessible? I did a lot of international work in my career, and I've seen perforation guns get held up in customs and not be able to enter the country. So they may not be accessible. Also, is the right size coil tubing available? It's not just is it available, are the well sites accessible to coil tubing? So you go to the Sichuan province in China, you can't get a large coil tubing unit up the mountains. So in most cases, they're operating with an undersized coil tubing unit trying to mill out plugs and things like that. And, is a workover rig a viable alternative to coil tubing? And is that available? So there's a lot of different, and then of course, what are the costs of those services? I remember doing some kind of study years ago, and coil tubing was something like $40,000 a day in Oklahoma and $120,000 a day in California. That's going to play a significant role in the bottom line economics. So not only do you have to consider what services are required, you also have to consider the logistics and the price and everything else around those services, because that can play a big impact. With the post-fracturing operations, first off, we have plug and perf. With traditional composite plugs, mill out is required. But once you've done it, you have a full production diameter, and you've also done a clean out run. So you're removing the sand and debris left in the wellbore as well. With the dissolvable plug, there's no post-frac requirement, but you do have the clean out optional. And in most cases nowadays, operators are still preferring to do the clean out run with the dissolvable plugs, just to make sure they're gone and to clean up any excess sand and wellbore debris that may be in the well and may hinder production. The ball activated systems, there's no post-frac requirements, but you are going to have production diameter restrictions. So if that's an issue, you can mill out the seats. And with the coil tubing activated systems, with standard sleeves, there's no post-frac requirements. And you have the full production diameter, but you have the clean out optional. And in most cases, they do go ahead and do the clean out because they already have coil tubing in the well. So once they finish fracturing, they just do a quick trip to the toe, circulate, clean out any sand, and then pull out a pole. And if you have the reclosable sleeves and you've closed them in the initial frac, then you are going to have to go in and open sleeves, open those sleeves for production. And then refracturing options. So we didn't have time in this presentation to talk about refracturing, but I'll hit it just the highlights really quickly. So with all of the refracturing options, diverters can be used on any of them. Straddle isolation, expandable liners, tubing strings can be used on any of them. And then, of course, the reclosable sleeves is only for the ball activated and the coil tubing activated systems. But the caveat there is if the reclosable sleeves are installed. If you have the non-reclosing sleeves, then that's not an option, obviously. So with diverters and straddle isolations, you may be able to get multiple refracts, assuming that you have a wellbore integrity. With the expandable liners, the tubing string setups, it's likely only one refract because you've reduced the diameter and added additional casing strings. Now, if you use the tubing string with the dissolvable gel, theoretically, you can get multiple refracts, assuming that you maintain wellbore integrity. Because you run the additional tubing string in, you isolate it with gel, you dissolve the gel afterwards, and then you remove the additional tubing string. So as long as your initial wellbore holds up, you should be able to do that multiple times. And then with the reclosable sleeves, you get multiple refracts, assuming that you have sleeve integrity. So once again, if the sleeves will hold up and open and close multiple times, you can do that. One of the challenges, though, if open hole isolation is used in the original completion, how effective is the refract with any of the options? So because you've just isolated large chunks of the well, and that may not match your refract design or your modern completion design. And this is just everything we discussed side by side. All right, cover this last bit really quickly so that we can go in Q&A and try to stay on time. So first off, multiple fluid entry distribution through clusters. Once again, the basic frac design, 90 barrels a minute through 3 clusters is 30 barrels a minute per cluster. If you're doing single entry though, and you want 30 barrels a minute per injection point, then you just pump 30 barrels a minute at surface. So this is a case history from the Granite Wash. 2 different wells. Well A had 10 stages with 3 clusters per stage. Well B had a 30-stage coil tubing activated system, so 30 sleeves. And the frac spacing was the same. So you had 165 feet between sleeves and 165 feet between between clusters with plug and perf. The rest of the variables on the frac job are virtually the same. Where you start seeing the difference, though, is the average frac rate. So with the plug and perf, because they're going out of 3 clusters per stage, they required 99 barrels a minute, whereas in well B, with the single entry, they were only at 40 barrels a minute. Now, if we go back to that basic theory of hydraulic fracturing, 99 barrels a minute out of 3 clusters, that design is 33 barrels a minute per injection point, compared to 40 barrels a minute per injection point. So this is arguably a more aggressive frac job, but look at the horsepower requirements. Well A required nearly 21,000 horsepower, whereas well B, with the arguably more aggressive frac job, required only 7,000 horsepower. And that can lead to a significant savings on location. Now, this is another scenario that happens relatively frequently. The Permian Basin is a good example where you have multiple target reservoirs and you have other target reservoirs around it, or maybe even a saltwater bearing zone around it. So the problem with multi-entry, even with the limited entry techniques, even with diverters, we only have limited control on how the formation allows the fractures to grow. And that can be problematic. The first one is pretty obvious. You breach into a saltwater zone and start producing too much water, then that significantly decreases the value of your well. The other issue is, what if you breach into target reservoir number 2? So you may still get a good well on this well here, but what happens on the overall field development when you come back 2 years later to develop target reservoir number 2 and you realize that you've been depleting from it the whole time? And ultimately, that probably means that you were not effectively producing target reservoir number 1 either. Now, with single entry, by no means am I claiming that you have direct control of the frac height, because you don't. It's still it's formation dependent, but you have direct control over how much fluid goes into each injection point, because it only has one injection point to go out of. So that gives you indirect control of your frac height. So hopefully, anyway, it gives you better control and you stay within that target reservoir. And then you can couple that with some real-time monitoring with microseismic or fiber optics or something like that, and try to help ensure that you stay within that reservoir. Let's see. So for time purposes, I'm going to skip over this real quick, especially if you've taken my class before, you've seen those. I want to get into let's see. Yeah, this will be good. All right, so let's step back and look at appraisal phase. So the objectives here are a little bit different because the operator just doesn't know this formation yet. So the objectives are going to be to gather as much data as possible and learn the formation in the field. So the additional risk associated with these types of formations, or this phase of the asset life cycle. Uncertain of your stage placement once you're finished drilling. Maybe you want to take some time to take a scientific approach. You also have a much higher risk of poorly drilled wells and a much higher risk of screen outs, just because on both of those you don't know how to fracture and drill this well yet, or this formation. So your ideal completion would be one that you can adjust the stages on the fly during the frac job, no increase in the completion diameter, full bore diameter in the completion, and that points us in the direction of plug and perf, maybe even the coiled tubing activated with sand jet perforator. But once we get to the development phase, the objectives are different: cost savings, efficient operations, and maximizing your production. So what are our completion options? We have the ball activated completion systems, with the highlights being the nonstop fracturing, the improved logistics, and the overall efficiency. You also have the coiled tubing activated system. So maybe you're in a reservoir where it's just really difficult to dial in that frac recipe and you have screen outs frequently. This may be a better system. Also, because of the single entry, if you need to contain your height, you have that indirect control of it. And if you're in a situation where you have a shortage of space on location, then if you can reduce the horsepower, you can save some space on location there. And then, of course, plug and perf. Plug and perf is still hands down the most common in the US. It's 95% of the market at least, maybe a little bit more. And now with the simultaneous fracturing operations, that really helps the inefficiency at surface. And there's always going to be exceptions to the rule. So when I was in the Marcellus, we had an operator that had done plug and perf for about a year. They did 15 wells or so with the ball activated systems. We followed up with them and they said it was great. The production was the same, no better, no worse, but they went from fracturing, taking 7 to 9 days with plug and perf down to 1 or 2 days with the ball activated sleeves. So they decided to change their entire completion strategy, go all ball activated sleeves. And then 2 weeks later, they called and canceled the order. What had happened in those 2 weeks is they lost their water supply. They only had enough water to fracture 2 stages per day. And if you take away the nonstop fracturing benefits with the ball activated completion system, plug and perf is the obvious answer there. It's much cheaper if you can't fracture fast anyway. So, I just want to remind you that these are general guidelines and there's always exceptions to the rules. So, and they, going back to this slide here, after one of the courses I taught recently, about a year ago now, I guess, a student came up to me after the course, a Canadian operator, and this was a pretty unique scenario. They were in extreme northern Canada. They could only access these wells 4 months out of the year, roughly, because they had to wait till winter for the marsh to freeze over so they could actually get access. So he comes and brings me the slide and says, well, my company is doing the ball activated systems, but you recommend the plug and perf for appraisal wells. And I was like, well, let's go through your scenario. So let's go through the risks I call out here. First and foremost, are you going to do any experimenting with stage spacing? And he said, no, we're doing geometric. We know how many we're doing. I said, okay, well, so that's not an issue. Do you have any experience drilling wells in this formation? And they said, yeah, we've drilled 8 wells and no issues. And I was like, okay, so that's not near as much of an issue. What about, with screen outs? Because they were only using the geometric stage spacing and they were only going to use 25, maybe 30 stages, I think. And so because they had less than 30 stages, then the coil tubing could get through the ball seats because of the larger diameters. And because they were out in the middle of nowhere and had limited access, they already had coil tubing on location. So that's not an issue. They could recover relatively quickly. So that points in the direction of the ball activated system. So, and the additional intangible there is that company had a lot more experience with the ball activated systems and other plays. So their crews were familiar with it, their people were familiar with it, and that was their preferred system. So there's a lot of other factors like that as well. So I will cover this and then we will go to Q&A to try to stay on time there. So this is, effect of the downturn in the U.S. And we're, I'm referring to the 2015 downturn, not the current one. So as you can imagine, this is going to have a drastic effect on completions as well. So we'll look at the U.S. Bakken. So in 2015, when the downturn hit there, so beforehand, operators had 1 year between drilling the well, fracturing it, and putting it on production. When the downturn hit, the state of North Dakota extended that to 2 years. So there were a lot of prominent Bakken operators that publicly stated that they would not be fracturing wells until they either saw oil prices they liked or until the 2 years was up. So the unique thing about completions is the completion cost of the actual equipment actually goes on the drilling rig budget because it's ran with the drilling rig. So the wellbore construction cost, if we do a breakdown here, if you cement a 10,000 foot lateral, it's about $50,000. 50 sleeves, ball activated sleeves, $150,000. 50 open hole packers, $150,000. And 50 coil tubing sleeves, $150,000. So if we just assume $3,000 for the sleeves and the packers each, that's where we get those numbers from. So the overall wellbore construction cost, if you did a 50-stage plug and perf, you only need the cement, so that's $50,000. If you did a 50-stage open hole, you need the sleeves and the packers, that's $300,000. 50-stage coil tubing system, cemented, that's going to be $200,000. 50-stage open hole coil tubing, that's going to be $300,000. And a 50-stage open hole plug and perf, that would be $150,000. So, if you're an operator and your strategy is to drill but not complete, here plug and perf is the clear choice. I mean, you're talking about saving millions of dollars on a matter of a few wells in a time where cash is king, and you're saving as much cost as you can. So it's clear that it's doing that. Now, the other kicker is that's not a 50-stage plug and perf system. Like I said, that's a blank wellbore. That's an open canvas to do whatever you want to with the well. Whereas all of these other systems are actually a 50-stage system. So with this system, they could run a 25-stage system with more clusters. They could run a 100-stage system, whatever they wanted to do. So I think for the most part, this was actually an accidental benefit that they kind of stumbled upon. And they were really focused just on lowering the wellbore construction cost initially. So I'm going to end my presentation there. I'm going to do a quick 2-minute thing, just because if you've stayed on this long, which I see several have, I want to share this with you, what I've done recently. So this is actually on my website here for the new course. So I wanted you to kind of just see it, how it's broke out. So if you're interested in it, you can do it. So you've got 2 courses here. So first off, this is a lunch and learn. We covered a little bit more than what's in here today, but it's free if you want to go back and review it later. And the overall course is my full day course here. Right now it's $100 per year for the subscription. So you can go back and review it anytime you want during that year. And what I think is unique about this is I intend it to be kind of like a dictionary. So it's broken up into small segments here. You can see each of the videos and it's 2 purposes. First and foremost, I'm sure I've been talking for an hour and a half now. I'm sure a couple of you have nodded off during that time. I know I do when I'm constantly listening. But here you would watch this 2-minute video. You would have to stop, move your mouse, and click on the next one. So it's for attention span in the original one, but it's also so it's easy to go back and use this as a dictionary in that later on. So if you need to know what you needed to, if you had a question about hydraulic set packers, it's easy to find this video rather than going through 6 hours of nonstop video to try to find this 2-minute and 42-second segment. So anyway, I just wanted to kind of briefly introduce you to that. You can find that at the website I've been talking about, uog.training. And with that, I will hand it back for questions and answers.
Okay, Aaron, we got a few questions, quite a few, I should say. So keep that in mind. I think we have something like 15 questions here.
Oh, okay.
And some of them are just comments, but we'll go through them here. The first one is from Herman Vaca. Can you please comment on your experience with various proppant mesh sizes and embedment issues?
So well, I don't know exactly from what angle you're looking at. So I mean, the larger the proppant, the less embedment you have, just because of the contact area. And you know, I'm assuming you just kind of called it proppant, so I'm assuming you're talking about natural sands. But you know, you could always use some of like the plastic proppants, the ultra lightweight proppants as well. And theoretically, those have a little bit less embedment issues, just because you know, when the proppant crushes, instead of just crushing it, it can actually bow out and increase the contact area as well. And then, of course, the other thing is the resin-coated proppant. So you can bond the proppant pack all together, and it helps distribute the load throughout the proppant pack. You know, it's just kind of like the bed of nails, right? You step on one individual nail with your foot, and it pierces right through. But if you lay down with your entire body on a bed of nails, it helps distribute the load, and it doesn't puncture through your skin.
Okay, next one here is from Francisco Pineda. Aaron, thanks for your presentations. I guess this is just a comment. You're all, I have to skip town. And he had to leave early, and he was just saying goodbye to everyone. Yep. Scott Myers has a question regarding frac fluids. What is the chemistry of the frac fluid, aka slick water? And is residue from frac fluid considered in the choice of friction reducer?
Yes.
Frac gel?
So I'll kind of give you my short answer. And I think maybe with this one, we could, if we have time, whoever's left over afterwards, could maybe try to address it in a little bit more detail. Yeah, so the slick water, it's a mixture of water and friction reducer, essentially, at the end of the day. In some cases, operators do call linear gels slick water as well, just because they don't have a lot of viscosity. And the only difference there is you're going to have some kind of like a guar that add a little bit of viscosity. So, and the short answer, once again, to the other part of the question is yes, it is considered. It gets beyond my expertise. So maybe we can kind of open that up for questions after the rest of them and see if anybody else has some thoughts. Does that sound good, Alex?
Sure. I think that's very good. And I guess, you know, if there's a follow-up, you know, the person that made the question can do a follow-up on the audio. The next one here is from Slavko, and I'm not sure if it's a comment, might be just a comment, but if you run full cycle economics, including acreage acquisition cost, and he gave an example between $20,000 to $90,000 an acre, break-even cost is high, and for some plays above $60 a barrel.
Yeah, and for some plays, for sure. I mean, in 2015, we saw the same thing, right? I mean, the Tuscaloosa Marine went out of the window because it was too expensive. I think at the time, maybe the break-evens were, or at least it would require something like $90 to $100 oil to produce because it was so clay-rich and the infrastructure wasn't there. So for sure, there will be those. And I think everybody on this call knows that there were a lot of operators that way overpaid for some acreage in the Permian when it blew up. So I'm not saying that that's across the board that everybody survives in the U.S. shale by any means. But, some of these overpaid acreage and if these companies go under, I think the Chevrons, the Exxons of the world are sitting there drooling, waiting to scoop up that acreage at a premium price. And I believe that they will make it work and economic.
Okay. And people can follow along on the chats because there's some I guess there's some recommendations here, like this next one. They're asking about this is P comment, saying that the chemistry very variable.
Yeah,
and he gives a website, ballotpedia.org, slickwater frac, and you can see that on the chat if you want to follow that website. Jorge Pinal asks, do you see any advance if the rig itself would have 15,000 psi capability to pump and seal the stagers as with an inflated packer from the bottom up?
Potentially, it really kind of depends. I mean, I think that's going to boil down to cost per day of having that rig that rig with that capability versus the cost of a frac spread. So I think that's where that's going to boil down to. If it's more economic, then sure. I don't know what the price of a rig with that capability would cost though, and the day rate on that compared to a frac crew.
This again, P comment. How do you control the fractures so they do not penetrate beyond the shale?
Well, it's a little bit of art and science, as much of an art as it is a science there for sure as well. You try to monitor it the best you can. I think one thing, well, I'll say it, but I was going to say I think everybody in the industry will say it, but I don't think some of the modelers would say it. But the reality is of our modeling in these plays, it's a good educated guess, but we know it's not accurate either. So it's a great starting point. But the reality is we still have a lot of calibration to do for our models. So yeah, we just have to, I think single entry points is a good start on that, and potential monitoring as well. So, and a lot of that just depends on, on the formation and whether it has good frac barriers surrounding formation. So in some cases, there's a good enough frac barrier that it contains it within that target reservoir.
Okay, this is from Scott Myers. I believe it's a follow-up. What I meant by chemistry is specifically what is the most common base gel? A polyacrylamide, I hope I pronounced that right, a gluon or a cellulose or other, all of which will have varying degrees of refinement, which in turn contain varying degrees of insoluble residue. So what's the most common, noting that most of those materials function as both viscosifiers and friction reducers?
Yeah, but sorry, is there I don't think there's a question in there, is there?
I'm not sure. Well,
Oh, well, I guess
there's
there
two
is
questions.
technically. Yeah. So this is in response to the other chain. So why don't we kind of get through the others and open it up
Okay.
to discussion?
All
Yeah.
right,
So
we'll do
that's,
that.
yeah. Okay.
Okay, Shahid Haq, just thanking everybody as a comment, as well as Carol. And yeah, we are recording this, and we should be able to have access. Let's see, and I think I'll get more. Yes, we have both presentations will be available on YouTube. See a lot of just thank you. I guess people leaving the session.
Yeah. Yeah. And you're welcome, everyone. Anybody that commented that.
Okay, and I'm just seeing here that Carlos wanted to take the closing Q&A. So Carlos, are you still there? Do you want to?
Yeah, there's one more question there from Sergey at the end.
Yeah, I see it. The question is additional environmental impact per cubic foot of gas or barrel of oil with unconventional versus cubic foot of gas in conventional fuels. And I don't know, Sergey. I don't know the answer to that. We can kind of open that up and see as well if anybody else. Since we do have a couple of people still on, I did actually kind of want to ask you guys a question. If you could respond in the chat before we open it up. So I've been thinking a little bit about this week, or this week I've been thinking about this, potentially offering a new course and diversifying myself a little bit, maybe even out of oil and gas some. So you guys have all seen the style I teach, right? It's very visual, things moving. And overall, that's a relatively simple. It's all PowerPoint animations and shapes and stuff like that. Would you see any benefit? Because each of you have your own expertise as well, right? So do you see my presentation and think, man, I could really animate my stuff? And would a course on how to do that in PowerPoint be useful to you?
I would say by many, yes, Aaron. A lot of, I say a lot, but a few people that know that I know you, for example, that do presentations, they use different people's presentation for their own, and obviously you have to give permission for those, but I would say yes.
Okay. All right. And okay, yeah, we got one more yes. So, okay. Good deal.
Yes, definitely.
Awesome. Thank you.